hopefully saw the announcement sent last week. Hopefully you see that. Completely lost it. So we're looking. There we are. Want to make sure, and I asked somebody in the last time, keep an eye on that screen over there. Make sure I got what I'm talking about on the board is actually where what's being recorded. I try to keep track of where I am, but I need to zoom in on what I'm doing, or else you're not seeing it. Okay, so I'll post it in the announcements. You should get an alert when I post something in the announcements. And in the announcements, there is the assignment sheet for chapter 5A, first part 5. And I also sent you this blank unit circle, which looks like this. And we're gonna do a little bit of this blank unit circle today. And we can't do everything yet because it's not time. When it's time, I'll tell you. From all else fails, extract from the other documents. Sorry, I have OCD. I get a little. It's not perfectly. Okay. As much as I have to have things so you wouldn't know by looking at that. All right, so back to the announcement. So those got an email from Math 4A tutor, Sakila, tutor for Math 4A. Mondays and Wednesdays from 4 o'clock to 5 o'clock, online via Zoom. This is her Zoom link. And she also has a QR code. And I will post this in the announcements before I leave school today. So this will pop up in your announcements. And this is how you can get a hold of her. And it looks like she's only doing it via Zoom. I don't know when her times are actually on campus, but this is her Zoom time. Mondays and Wednesdays from 4 to 5. You can still walk in at any time in the STEM Center. Remember my office hours. I know it's early, 7:30 to 8:20, Monday through Friday, Monday through Thursday. Tuesdays and Thursdays, I have a time in between my classes. I don't have a time in between my classes here. But if you show up, 10 minutes before class, if I'm not trying to scramble and get things ready for you guys, I can still try to help you. I can always stay a little bit later. If you need me to stay a little bit later, I can try to work that out. Just try to communicate with them know. And then on Fridays, if you want to Zoom with me on Fridays, it's from 9 o'clock to 10 o'clock. But you got to let me know, and I'll send you a Zoom link, and we'll just, do it. But there's lots of help. It's all free. Take advantage. Don't fall behind. I'll send that. Not closed. Angles. I introduced what a radian was, but we're not going to actually do much more with radians until a section from now or so. No, I take it back. And this, I see I've got to remember which section things are. Sometimes my head moves. But plain. So if you didn't print out the blank unit circle for yourself, I made a report. In fact, I made a few for you. So you have on one side. I told it to print back and front back. Nobody ever listens. The key to survival is knowing your unit circle. It really is. When you were growing up, you did something called math facts in elementary school. 100 addition problems in 3 minutes. 100 subtraction, 3 minutes. 100 multiplication, 100 division. And they would time you. And that's when people started hating math. Quit timing me. Well, the reason why is because it was memorization. You weren't actually doing the problems anymore. They were just memorizing the first answer 7, the next answer is 12, the next answer is 3, the next answer is 4. And because they weren't difficult problems, they were just trying to see how fast you could go. It's not the best approach. I don't want you to memorize the unit circle. I want you to be able at any time to make a unit circle. Because it ain't that hard. It's just a process of, hey, if I know 2 or 3 things, I can do the whole thing. That's all you need is a couple of things, and then you can complete the puzzle. And that's what this is. It's a puzzle. And we're going to make pieces of the puzzle all fit together. And it's going to save you behind because what you need to know, much of it lies right here on the unit circle. So I'm going to give everybody 2 copies. In case you make mistakes, you can always print more. And if I have more, I should have printed those sides. I don't know why I didn't. I'm sure if I asked my wife, it was my fault. You ever do the whole, I'm sorry, and then they ask you, what are you sorry for? Man. I'm sorry because I just don't want to argue anymore. I should not say these things while I'm doing it. Well, that was convenient. I ran out just as. Oh. Hey, I got pretty colored ones. Let me give you 2 more of these. So you got plenty now. You got all sorts of them. Use them or not use them. But again, these will be. So I would be messy on the black and white and pretty ones in color. I know I should have supplied my crayons. I knew I made copies. And does everyone have a copy of the homework? Okay. Remember, homework's not due until the day of the test, and follow the directions that are on the front, cover page of the homework, and that's how we'll take care of it. We'll talk about that more and more as we approach to our test date, which I'm not exactly sure when that's going to be yet, which is not bad. Okay. So, degrees. In a circle, thanks to the Babylonians who love the number 60. Okay, sexagesimal, not sex because of sex, the sexagesimal system based on base 60. 360 degrees in a circle. Why? That's just got the ball rolling. I mean, they came a why 12 inches in a foot. Well, somebody had to decide where the inch was going to be. What was it going to represent? Somebody had to do something. Why make it 12? Why not? Why don't we cut up that foot into 10 pieces? Wouldn't that have been a lot nicer? Because divided by 10 is a lot nicer than divided by 12. Okay. Well, then we would have been the metric system, and that's not a metric. That's a problem. Okay. But here's the deal. You know what's better about the metric versus the standard measurement system? The foot. The foot is a couple of notches on a very resilient piece of metal kept in a vacuum in Geneva. The standards, the measurements. Where they basically keep everything that's supposed to tell us what a minute is, a second is, and it's where we keep under guard, because if we lose those things, we don't know what a foot is. Because this ruler is made of wood. If you heat it up, it expands, and when you get it cold, it shrinks. So the measurement of a foot here, what represents a foot, could change. It could warp. So yeah, it still says 1 foot on it, but if it warps, that measurement of 1 foot is no longer a foot long. Make sense? So the actual foot, standard foot, is kept under lock and key in a nice vacuum in a very, I think it's a beryllium bar. Right? I'm not sure. It's been a long time since I've talked about this, but that's what it is. Versus metric. Metric is repeatable under any circumstances at any time. It's the measure of the spectrum of argon gas. You do that anytime. It's not going to change under the conditions of the weather. Okay. Metric versus Fahrenheit. Guy named Fahrenheit went outside. Ooh, it was kind of cold. I'll mark that 0. Boy, it's kind of hot. Well, that must be like, mark that 100. And then slices it up. He divided by 10. Well, there are places that were colder than where he was. So now you have places that are now negative Fahrenheit degrees, or degrees Fahrenheit. And places that are hotter than where he was. So you have places like Fresno and Madera, they get to 110, 111 degrees. Okay. Celsius, 0 degrees Celsius is the temperature at which water freezes at 1 atmosphere pressure, scientifically. That's it. So at 1 atmosphere pressure, the temperature when water will freeze, that's 0 degrees Celsius. 100 degrees Celsius is the temperature where water boils at 1 atmosphere pressure, repeatable. What temperature Fahrenheit does water freeze? 32. Positive 32 degrees. It's not that cold. And what temperature does water boil? Fahrenheit. 212. So, I mean, that's a big old stretch. So it's like, what's going on? Our standard thing is, I have no idea what I'm supposed to feel when they tell me it's going to be 27 degrees Celsius. I have no idea what that means. If somebody says it's 8 kilometers from here, my brain cannot wrap itself around it. So I don't understand how far 8 kilometers means. Is that like, can I walk there? Should I drive there? It doesn't process because, I grew up in the 70s. We tried. to switch over to the metric system. We would have nothing to do with it. We ain't doing it. But in this class, you're gonna have to switch over from degrees into other measurements for circles. We talked a little bit about it last Wednesday. But first, let's deal with the degrees. So 0 to 360 in one revolution of a circle. So if we start here, we're at 0 degrees for an angle in standard position. Now we call standard position when you're on the XY axis. You know, I tell you these stories to give you some inside knowledge. You can at least go, fascinating. Here we go. Oh. All I hear is, huh? See, I'm going to tell you stories about basketball games. Standard position. Vertex of the central angle is at the origin. The initial ray, the initial side of the angle is along the x-axis. And then it opens, like we talked about last week, counterclockwise. So 0 degrees means the initial side and the terminal side are on the same, they're the same ray. Because that would be an opening of 0 degrees. Ain't got no opening. Okay? So then we rotate up. So let's do this. One revolution all the way around brings us all the way around. So that's 360 degrees. Okay? And then you do some slicing. Time to do some slicing. So the first slice happens, let's go halfway. So if a full circle is 360, then halfway, this is where 180 degrees is. And you're looking at what we call a straight angle or a linear. The rays are called a linear pair because when you put the two rays back to back, they form a straight line, which is 180 degrees of opening. So a straight angle, the rays are a linear pair. So that's 180, halfway. And then let's do a half of that half. So if we do half, we're only opening up to here. So this is 180, half of 180 straight up would be 90 degrees. So straight up is our 90-degree angle, otherwise known as a right angle. So the vertex would have to be right here again, the origin. And when you're straight up like this, you have a 90-degree angle. And did I go over that when you have a right angle, 90 degrees, when you draw something and you want to make sure that everybody knows that it's 90 degrees, in your picture, you either need to put, hey, 90 degrees. Because if you don't put 90 degrees, just because it looks like it doesn't mean it is. Maybe that's 89.5 degrees of opening. So if you're not, specific about what you're drawing, nobody's ever going to know. You never assume. Or this symbol, that's a symbol for a right angle. If I draw that little box at the intersection, hey, that's a right angle, 90 degrees. And that's better to draw a little box than actually writing the number 90 degrees. Okay? That kind of is a little too simple, simplistic of a picture, but let's look at two lines that intersect like this is. Not as easy to tell as whether or not they are a 90-degree angle until if I put that little box in there, okay, they're 90, that's a right angle, that's 90. We also know word that represents two lines that do that, they're perpendicular lines. If two lines intersect and form a right angle, they're perpendicular to each other. So 90. So now we know that every quarter of the circle is a 90-degree angle. So 90, 90 is 180. So down here, another 90 from that 180 is going to put us down there on this ray at 270 degrees. Because when you open up all the way to here, you've got 90 and another 90 and another 90. And 3 90s make 270, and another 90, 4 90s would make 360. There's 4 90s and 360. Let's be clear. If you don't put the degree symbol, then it's something other than degrees. So if you mean to have degrees, you got to put the degree symbol on your angles if you're labeling it with degrees. Otherwise, without a degree symbol, it's a different measurement. We'll talk about that later. Okay, so the first cut, 360. The next cut, you cut it in half, 180. Then you cut the 180 in half. Okay, and we get 90. So we get the multiples of 90. So the next cut is we do another half. But the next half we're going to make is right here. So you know this whole thing is 90. And if you cut 90 into 2 equal halves, then this angle going up to the first half is how big? That's at 45 degrees. Half of 90 is 45. And then the next half on top of that would be another 45. And 45 plus 45 is 90. Good. And all the puzzle should fit together. And then you do another 45. 90 plus 45. This point right here is at 135 degrees. So in the quadrants, in every quadrant, that halfway angle mark, they're all multiples of the 45s. 135 plus 45 takes us to 180. 180 plus 45 is exactly 225 degrees. 225 plus 45 takes you to 270. And 270 plus 45 takes you to 315 degrees. And you know you get it right if you make sure you end up right back at 360. 315 plus 45 adds up to 360. It should always take you right back home. And that's all those cuts. Notice they all end in a 5. All the other ones don't. The only ones that end in 5s are your 45-degree angle cuts. These 45 degrees is a very special angle. It's a very important angle. And so are the next two, of course. Because it's on the unit circle, you see how it's divided up? All of these are the special ones. I'm not going to make you memorize what's 127 degrees. Not that one. Be ridiculous. But there are certain ones that make our lives happy. Or at least tolerable. So the next one is no longer going to be a half. And the reason why we don't go to half is because of this. In geometry, you learned about 2 special right triangles. 2 special right triangles. 45, 45, 90. The 45, 45, 90 right triangle Over here, we're at a blank spot to in a 45-45 right triangle. 45-45 value. First of all, if two angles are equal, then the two opposite sides would be. So that's 45 degrees and that's 45 degrees. If these two sides or angles are equal, then the opposite sides would also be equal. So it's automatically going to be an isosceles right triangle. Automatic. If it's isosceles, if this side is x, then this side would have to be x. Now, according to the Pythagorean theorem, I don't ever use a squared plus b squared equals c squared, because that's only going to work if a and b are labeled where the legs are and c is labeled as the hypotenuse. You never know. Maybe c is a leg and b is the hypotenuse. And I get students that will always put it in the wrong order because the picture is labeled differently. You have to pay attention to who's labeled what. So what I write is leg squared, the square of a leg, plus the other square of a leg is equal to the length of the hypotenuse squared. So here, this is my hypotenuse. The side opposite the right angle, the longest side in the triangle. Leg squared plus leg squared. X squared plus x squared is equal to the hypotenuse squared. 1x squared plus 1x squared, that's 2x squared, is equal to the square of the hypotenuse. So the hypotenuse is equal to, take the square root of both sides. The hypotenuse is equal to, now what you have right here is the square root of 2 times the square root of x squared. You can split that up. The square root of x squared is just x times, that doesn't simplify, that's the square root of 2. So the length of the hypotenuse up here is x square root 2. It's the length of the leg times square root 2 always. So you know it's a 45, 45, 90. If you have a right angle and that's 45 degrees, and I'll tell you that this side is equal to a 5. So two things are going to happen. Number one, I know it's 45, 45, 90 because the three angles in a triangle add up to 180. Since this is 90 and that's 45, then I need another 45-degree angle in order to make 180 degrees, which means it's now isosceles, which means this side has to also be 5. I don't need to do the Pythagorean theorem. Since it's 45, 45, 90, the hypotenuse is just square root 2 times this leg. So it's square root 2 times the 5. That's all you got to do, square root 2 times 5. So 45s are important angles. That's why we put them on the unit circle. The other special triangle that you learned about, 30, 60, 90. 30, 60, 90. Now, I'm going to give you the rules for the 30, 60, 90, then I'm going to show you why it's true. Camera pan. Where have I put it? In a 30, 60, 90 triangle, so here's my 90 degrees. You got the hypotenuse. These are both legs. The legs of a right triangle are the two legs that form the right angle. Now, obviously, they're not congruent to each other. They're not equal. First of all, this angle looks bigger, so I'm just going to use the looks here. This angle looks bigger than that one. So if it's a 30-60, 90-degree special right triangle, I'll label that one 60, and this one would have to be 30. Now, the biggest reason is this. In a triangle, it's called the Triangle Inequality Theorem. The biggest side is always opposite the largest angle. So the longest side, the hypotenuse, would have to be across from, opposite, the 90-degree angle. The smallest side would be opposite the smallest angle. So the smallest side of the triangle would have to be opposite the 30-degree angle because that's the smallest angle. Always. So what we do is we call these, because they're legs, this would be the short leg on this side, and this would be the long leg over here. Opposite 60 is the long, opposite 30 is the short. The rules for 30, 60, 90. And it goes right through the short leg. It's all about the short leg. If the short leg is X, the hypotenuse is twice as long as the short leg. It's twice the length of the short leg, always. So if the short leg was a 3, the hypotenuse is a 6, no matter what. I don't need to plug stuff in. It's all 3, that's 6. If it's an 8.2, then the hypotenuse is 16.4. You just double it. The long leg is equal to square root 3 times whatever the short leg is. It's X times the square root of 3. So if that's a 2, this is 2 times square root of 3. If this is 8.2, then this is 8.2 times the square root of 3. That's the ratio. No matter how big I draw this thing. If this is 4,000, this is 4,000 times square root of 3. If that's 4,000, that's 8,000. They have to stay in the same ratio to keep a 30-degree, 60-degree angle right there. Because if the sides get longer, or sorry, if the sides get longer, they have to grow at the same rate to maintain the 30 and 60-degree angle. Just it. So here's why. You start with an equilateral triangle. Definition of an equilateral triangle: a triangle that has 3 equal sides. All 3 sides are equal. If all 3 sides are equal, then automatically it's also equiangular. All 3 angles are equal. If all 3 angles are equal, then 180 divided by 3, each angle has to be 60 degrees. See, we had to come up with a 60-degree angle somehow. If I'm going to try to figure out this, got to come up with 60 degrees somehow. Then, we're going to say, for the sake of our numbers over here, our demonstration, we're going to label the length of all 3 of these sides a 2x. They're 2 times whatever x is. Just so it works out nice. The next thing you would do is you would bisect you would draw a perpendicular bisector from this vertex to the opposite side. Now, as I said last week, back in the old days, they just had string and a stick in the ground, and they would bisect it. Did you do constructions in geometry when you went to high school? Compasses, and you didn't actually measure angles, you actually bisected angles, you drew congruent lines with compass and straight edge. You never measured anything, you constructed it. Well, they didn't have compasses, they used string. And they're able to do the same thing that you guys did, but just using string. Okay. I have a compass over here too. But unfortunately, my rubber bands broke, so I would have to, we used to have something called chalk, and chalk goes in here. But I can't use chalk on the white. So I would rubber band dry erase pins for that. But again, sake of time, I'm going to draw a perpendicular, straight, right angle, bisector. It cuts the opposite side into two equal pieces. Perpendicular bisector straight from that vertex angle. Now, something happens when you do that. First thing, it's a bisector, so it cuts this into two equal pieces. So if the whole thing was 2x, how big would each piece be? They'd be just 1x each. Okay. Since it's perpendicular, this is 90, and that's 60. 90 plus 60 is 150. So this right here has to be 30 degrees, which means since it was 60, it also bisected the angle up here. That's also 30. So it actually bisects the angle at the top, bisects the vertex. But what it creates is, I'm going to pull this out of the picture. It now created the 30, 60, 90 that I needed. And this is 2x, and right away, you can see that this short leg is 1/2 of the hypotenuse, or you can say that the hypotenuse is twice as big as this short leg. That's an automatic revelation because it came from an equilateral triangle. Question is, we now need the long leg. So I'm going to use a variable. I'm just going to call it, since we like a squared plus b squared equals c squared, I'm going to just call it a. The Pythagorean theorem says a squared plus x squared is equal to the hypotenuse 2x parentheses squared, all of it. So a squared plus x squared is equal to 2x whole thing squared is 4x squared. You subtract x squared from both sides. A squared, 4x squared minus 1x squared is 3x squared. We take the square root of both sides. And the length of this long leg A is equal to 3 square root of 3 times x squared. The square root of that x squared, like it did over on the 45, 90, that will pop out in front. X, 3 stays in the square root, square root 3. This long leg, in terms of x, is just a short leg times the square root of 3. (30, 60, 90) is a very special right angle because it comes from what we call a regular triangle, a regular polygon. Anytime you have a regular polygon, it means all of the sides are congruent and all of the angles are congruent. So a regular quadrilateral is a square. A regular pentagon, all of the sides are like the Pentagon in Washington, all of the sides are the same length and all of the angles are 108 degrees. A regular hexagon, all of the sides are equal. Every angle is 120 degrees. You can have hexagons that are not regular. They just have 6 sides, but the angles can be different. The sides can be different lengths. But when it's a regular one, it's, you might want to think, back then they want to look for perfection, all 3 sides, all 3 angles equal. And from that, 30, 60, 90. Okay. So the next division that we make in the picture is the 30s. Thirties less than 45, so that's this right here. That's what 30 degrees is. And 30 is a nice division of the 360. How many 30s are there in 360? There's 12 of them. Remember that. If you add 30 again, that takes you to here, which is 60 degrees. You know what? I'm going to do that. That's where 60 degrees is. If you add 30 again, that takes you to 90. If you add 30 again, 90 plus 30, that's over here is 120 degrees. If we add 30 to 120, we're now at 150 degrees. And if we add 30 to 150, we're right here at 180. Add 30 to 180, this is 210 degrees. Add 30 to 210, and that takes us to 240 degrees. And then 240 plus 30, is that 270? 270 plus 30, that takes us to 300 degrees. And then 300 plus 30 takes us to 330 degrees. And 330 plus 30 takes us to 360. Right, that we started. Those are all the special angles in degrees that go around the unit circle. And when I'm saying unit circle, that will come into play, I believe it's section 1.3. Unit means it's one unit as a radius. So the radius is one. And it can be 1 foot, 1 centimeter, 1 mile, 1 yard, 1 whatever, but it's just one. And then if the radius is 1, it's going to show you, unit circle is going to affect triangles, and it'll all play in when we do trig, when we do the sine, cosines, and tangents. 1 is the nicest number to work with. It's also the loneliest number that you want to do. You're supposed to break out something. 1 is the loneliest. You know that. 1 is the loneliest number. Dan is called 3. I don't think they were mathematicians. You know the band Queen. Have you heard of the band Queen? You know who the guitarist for Queen is? Brian May. Amazing guitarist. He is has a doctor's degree, PhD, in astrophysics. When he was first joining Queen, he was a college student working towards astronomy, astrophysics. And then, he started to be a rock star for a while. And then he just completed his doctoral thesis. I believe it was in 2010. Okay. Not too bad. All right. Put that rock star money to use. I'm so impressed by everything. Okay, so important stuff. I'm just going to put it over here to the side though, so I can get it out of the unit circle I made. But I usually tell my daughter, I don't think Carrie Stiles has a degree in astrophysics. But then Brian May was in the last Marlin group. So. Keep that. Where did I put that? Get out of there. No. I don't want you either. Yeah, no. Okay. So as you can see, in quadrant 1, it's no equals between 0 to 90. Equal to 0 is on the axis. Equal to 90 is on the axis. Quadrant 1 is in between 0 to 90. Quadrant 2 is in between 90 to 180. Quadrant 3 is between 180 to 70. Quadrant 4 is between 270 to 360. Okay. Any questions? Yes. I need to put that thing on my wall. Should I do the queen stuff again? Okay. So in between 0 to 90, quadrant 1, 90 to 180, quadrant 2, 180 to 270, quadrant 3, 270 to 360, quadrant 4. This is going to come up all semester long. One of the questions you're going to see in homework, what quadrant are you in? Drawing your pictures accurately. What quadrant are you in? Why do you draw it like that? Why don't you draw it in the quadrant you're actually in? Saves a lot of heartache if you draw it in the correct quadrant. Makes all the pieces fit together. Okay? Accuracy. Acute angles, right angles, obtuse angles. We talked about straight angles and 0 degree or full revolution. So an acute angle between 0 and 90, not equal to 0, not equal to 90, but between 0 and 90. So it's a little tiny acute angle. No, that's not how you just, if you need to think of it like that, sure. But between 0 and 90. A right angle, 90 degrees. Obtuse angle. When again, teaching high school, I would hear people, other teachers in the home. Well, acute is tiny, so obtuse is like a fat angle. No. Exactly. Obtuse, and this is what, because I'm saying, that's why you look going down the hall, and I'll go, okay, I have a math degree. PE degree, teaching math, PE degree, teaching math, PE. Oh, coach. Between 90 and 180. So it's past the 90, but between, less than the 180. So in other words, it terminates in quadrant 2. Would terminate in quadrant 2. Straight angle, we talked about that, 180 degrees, and a full revolution, 360, which would look just like 0 degrees. If we said 390 degrees, 390 degrees would put it right back here because you would go past 360 and go 30 degrees more. So you're back in quadrant 1. Now, even though you're back in quadrant 1, the angle was 390 degrees. It's not acute. The actual angle includes the full revolution and the extra 30. Now, you can describe it using something called a reference angle. You can describe it using coterminal angles. They might be acute or obtuse, but the actual angles itself for acute and obtuse would have to be, right here between 0 and 90. You can't have something that goes all the way around and ends up between 0 and 90. The original is not. And we did coterminal last week. We're just adding and subtracting 360, right? Did that last week. And I am going to go over homework questions, so we'll actually do some with actual problems. Now, this part right here, I'm not going to test you on this. Complementary and supplementary. There are a couple of homework questions on it, and I'm going to describe it, but you're not going to get tested on it. Complementary angles. Two angles are complementary if the sum of the angles is 90 degrees. Or you might say, if the sum of two angles is 90 degrees, then they are complementary angles. So 40 and 50, they are complementary angles. 1 degree, 89 degrees. They would be complementary angles. Now you cannot use 100 and negative 10. Okay? Two positive angles are complementary. So you can't combine a positive and a negative angle and expect that to be an okay answer. So two positive angles are complements of each other if the sum is 90. Two angles are supplementary if the sum of their measures, positive angles, is 180. Two angles are supplementary, positive angles, supplements of each other, if the sum is 180. Okay. If two angles, if their initial and exterior side over here form a straight line, you make supplementary angles. You see it a lot in pictures. So if you know that this side over here is, I don't know, 70, then this one over here, you can just, if you know it's a straight line at the bottom, it's 110 because they're supplements of each other. They add up to 180. Complementary, C. Supplementary, S. Alphabetically, C before S. 90 before 180. Complementary goes with the 90. Supplementary goes with the 180. Whatever it takes for you to know which one is which, that's what you have to do. So we will handle a homework question that is dealing with that, but you're not going to get tested on complementary and supplementary. So I showed you last week that we define the measure of a radian. An angle measured in radians is a ratio. Theta in degrees, theta in radians is a ratio between the length of an arc of the circle divided by the radius of the circle. How many times can the radius fit in that arc length? Theta in radians. So there's the center of the circle. So there is going to be some arc on the circle that is intercepted by this radius and this radius. So R represents the radius. The arc length is the distance on the circle itself. This is the arc length. We use S for arc length. Don't ask me why it's always represented by S. Maybe because S is nice and curvy. It's the length of the curve. Let's call it that. I'm making it up. But S represents the arc length on the circle. Theta in radians. So the central angle in radians, theta, would be here. So theta in radians is equal to the length of the arc divided by the radius. How many times can the radius fit into that arc length? Maybe it can go in 5 times. So theta in radians would be equal to exactly 5. Maybe it can only go in 1/3. Maybe the arc length is a 1 and the radius is a 3. maybe this is a 1 and that's a 3. So in radians, theta would equal 1 over, it would just be 1/3 of a radian. Theta is 1/3 of a radian. Now remember, radians don't actually have any real units. We call them radians, but they don't have any real units. Because when I divide the two lengths, this might be centimeters, this would be centimeters. So 1 centimeter divided by 3 centimeters, the centimeters reduce completely. So you just have a ratio of 1/3. Because you're measuring an angle, what are we measuring it in? We're calling it radians versus we're calling it degrees. It's a different way to measure an angle. What I showed you last week was this. If we measure a full rotation, theta in degrees for one rotation is exactly 360 degrees. We know that. Just got done doing it. Okay, we just got done doing it. In radians, well, we know this. In radians, theta would equal the arc length divided by the radius. The full rotation around the circle has got a special name, circumference. Circumference of the circle. So this arc length that goes 360 degrees around, that arc length would actually be the circumference divided by the radius. Full circle. Now, the circumference has a formula. The circumference of a circle is 2 times pi times the radius of the circle. 2 pi r. So now I can say that in radians, theta is equal to the circumference 2 pi r divided by the radius, which is r. And that's where I showed you last week that 360 degrees in radians, the radii reduced, is just 2 pi radians. So 360 in degrees is equivalent in degrees to 2 pi in radians. The actual number 2 times the number pi. So pi is approximately 3.14159 or 3.14. Goes on forever and ever and ever. 2 times pi is about 6.28. Okay. So it takes approximately 6.28 as a number in radians to go all the way around to make that circle in radius versus 360 in degrees. And that's going to help when we do the second part of chapter 5, when we do all of the graphing, because then we'll be able to make an x-axis and a y-axis that are much more in scale with each other. Okay. So relationship. So in any case, whenever you have units, like units for degrees, a couple of different ways, or units for an angle, degrees versus radians, there's got to be a way to convert one into another. And you've got to have a conversion factor, like converting inches into feet. 12 inches for every foot. 360 degrees is the same as 2 pi in radians. But that's not the special one. That's not the one you want to know. That's not the one you're going to always want to use. Because you can actually simplify this. They're both even. Let's get rid of that times 2 and divide both sides by 2. We actually like to use this one better. 180 in degrees is the same as 1 pi in radians. That's our special. And so for right now, and we're going to continue working on the unit circle. We're not going to fill all of it in yet. I'm just going to fill in these pieces. So in degrees, 0 degrees, 90 degrees, 180 degrees, 270 degrees, and then back to 360 degrees. In radians, this would be 0 in radians, because if that was the angle of opening, so here's the radius, but the arc length has no arc length, it's 0. So 0 divided by the radius would be 0. So the radians would be 0 radians at 0 degrees. So that's 0 radians. Halfway around at 180 is pi radians. This is exactly pi radians. You just put pi rad. And then what did we do when we first dealt out all of the degrees? Then we started doing a little bit of half. And that's all we're going to do right now is just one more half. This goes to 2 pi radians. So let's look at this half picture. If this is 1 full pi for the half circle, then you divide by 2 to get this measurement for the 90-degree equivalent. So at 90 degrees, now remember, we're going to want exact values. We're not going to want decimals unless the directions, or I say in the homework or the test, give me decimals. Exact value. Pi is a number. The symbol pi represents the transcendental or irrational number. 3.14159 goes on forever. So to get this angle, all we did was divide the straight line, the straight angle, by 2. So you divide by 2. It's pi over 2 radians. That's it. Half a pi. 1/2 pi. So it would be, if this is 3.14, that's approximately 1.57. Every calculator has a pi button. You press the pi button, we want the whole decimal, as much as your screen will allow, pops up. So now every 90 is a 1 over 2 pi, pi over 2. So if you go pi over 2, this is another pi over 2. Pi over 2 plus pi over 2. 1 pi plus 1 pi, that's 2 pi over 2. And the 2's reduced, and that's why that's 1 pi. And then if you go down here to 270, so that's pi over 2 plus pi over 2 plus pi over 2, add another pi over 2. 1 pi plus 1 pi, that's 3 pi over 2. Because it's 3 of these half pi's. So this is the same as 3 pi over 2. For those of you that hate fractions, oh, you're going to have a different attitude in this. Fractions are going to be very, very helpful. And it's just a matter of looking at what we're doing from a different point of view. Okay. And then as you go 3 over 2 plus another 1 over 2, 3 pi over 2 plus 1 pi over 2, 3 plus 1, that would be 4 pi over 2, and 2 goes into 4 2 times. So right there, it's 2 pi. The puzzle fits, all the pieces will fit together. Okay. So you're going to come across a need for some formulas. I am not a memorizer. There's a few things that I don't not necessarily memorize, but I know. It's about knowing, not memorizing, or it's at least about being able to figure out what you don't know from what you do know. Memorizing just today just means you're going to forget tomorrow. So I'm not a very big memorizer. Plus, my brain is like Swiss cheese. It's got holes all over the place. Okay. I'm lucky that I got married on September 1st. Because that's a nice, easy, simple number to remember, 9-1. And in a decade, in a year that ended with a 0, 90. 32 years. Plus, it's also easier to do the math. How long have you been married? In the 90s. It'll be 32 years. Makes life a lot easier. Okay. Now, don't ask me how old my kids are. I have no idea. Well, my son's going to turn 31, I think, because he was born that next year. My daughter, though, was born on New Year's Eve. I really struggled with that one. She turned 27 this last year because she's off the insurance now. She's got to pay her own way. That's okay. She's married. Okay. I'm off the screen. So, yeah, but you didn't see the weight. She doesn't watch. She had enough of me. She did hear that hairstyle. She has seen One Direction. I don't know how many times she even saw BTS. I think that was once, if not twice. Oh boy. She grew up going to concerts, all because I took her to that first Weird Al concert. Now Daniel Radcliffe is going to play Weird Al in the biopic of Weird Al Yankovic. That's good. All right. In high school, I allowed her and her friend to go to Coachella twice. That's how bad of a parent. So, formulas. In geometry, how do you figure out arc length? In geometry, you did not know what a radian was. It was just a thing on a calculator. Hopefully your teacher said, make sure you're not in this radian mode, make sure you're in degree mode when you press the buttons. So in geometry, when you wanted to figure out an arc length, the length of a piece of the circle from, I don't know, here to here. And let's just say that this arc right here, that's about 90 degrees. Okay, and let's say that the radius is a 4. Well, the arc, the measure along the circle, this part, how far is it if you were to walk along the curve? You would have to do this. It's just a fraction of the circumference, because that's all an arc is. It's a piece of the circumference, it's a piece of all the way around. It's a fraction of the circumference. How do you figure out the fraction? Well, you know the entire circle is 360. So to get that fraction, it's this central angle, theta in degrees, out of 360 degrees. In other words, 90 degrees. Isn't not a 90 degree right here 1/4 of the whole circle? Because 90 over 360 gives me 1/4 of the whole rotation. That's how you make the fraction of the circle, fraction of the circumference. The central angle divided by the whole 360 part. So theta in degrees over 360 in degrees. Okay. Of the circumference. So then you would multiply times 2 pi r. times 2 pi r. So in geometry, you would have to do all this. S would equal 90 degrees over 360 degrees times 2 times pi times the radius is 4. So then we would go, all right, 90 goes into 364 times. So the arc length is equal to 1/4. 2 times pi times 4, that's 8 pi. So 1/4 of 8 pi, 4 goes into 8 2 times. The arc length is 2 pi units long. This is 2 pi units long. So let's say I gave you centimeters. This would be 2 pi centimeters in length. Because arc length is a length. That's my units. That's how you would make it work. Well, along comes the radians. Look how nice the radians are. First of all, we know that theta in radians. Now you notice every time I'm using theta in degrees, I gotta put the degree symbol. If you don't put the degree symbol, it's not a degree. You have to put the degree symbol when you mean degrees, otherwise it's not the same thing. Otherwise, it's a radian. Theta in radians is equal to the arc length divided by the radius. That's a formula. So remember, we want to know what's S. So theta is equal to S divided by R. How do I get S by itself? How do I get that S if it's divided by R? How do I just get the S? Multiply both sides by R. So R times theta is equal to S. So S, the arc length, is equal to what? I'm going to use the commutative property of multiplication, which means I can switch that order. Theta in radians times the radius. Look at this formula. Theta degrees divided by 360 times 2 pi r. And now look at the formula if you're dealing in radians. It's just theta, make sure it's in radians, times whatever the radius is. Now, you cannot plug degrees into here, because it won't work. That's radians. And you can't plug radians into that because it won't work, because they're different units and different measurements. Things would need to cancel out. So how big was 90 degrees in radians? 90 was what? Radians.
Pi over 2.
Pi over 2 in radians. So the arc length would be pi over 2, and the radius is 4 centimeters. And 2 goes into 4, 2 times. Pi times 2 is 2 pi. So these two guys are a couple of new friends. Put them over here. Theta in radians is equal to the arc length divided by the radius. And from this formula, you can get that the arc length is equal to theta, and I'm just making it a subscript so you remember it's radians. Theta in radians divided by, times the radius. Now, one other thing that's kind of interesting. If we take our old formula, our geometry formula. You take the old formula and say, all right, instead of degrees, I'm changing this theta into radians. So if I change my measurement into radians, so theta is now a radian instead of a degree. How do I know that theta represents an angle in radians? Pardon my English, but there ain't no degree symbol on it. That's how you know the difference. If there's a degree symbol on the theta, not degrees. If you don't have a degree symbol, it's in radians. That's how you know which one is which. Divided by. Well, if I'm switching to radians, it wouldn't be 360 anymore. What would it be? 2 pi. Because I'm switching to radians. 2 pi radians replaces 360 degrees. So I'm replacing my angle measurements with radians instead of degrees. Times 2 pi r. And then look at this reducing 2 pi divided 2 pi. And the arc length is equal to theta times r. Okay. Always. So when we do the homework, and again, I'm not big on memorizing, so I'm not. This is page 401 in the text. And it gives you formulas that you can memorize and apply to convert degrees into radians, radians into degrees. If they're not our special angles, if I ask you what is 50 degrees in exact radians? Well, 50 is not one of our special angles. 50 is not one of the ones that we're going to know by heart. 50 we would have to actually maybe show work for. So if I want to convert degrees into radians, it says multiply by degrees over 180 over pi radians. And if I want to convert degrees, sorry, I was reading only half of it. If I want to convert degrees into radians, I'm going to multiply by this. Pi radians for every 180 degrees. And if I want to convert radians into degrees, I'm going to multiply by this. 180 over pi. So there is a connection. It's about pi and 180 always being that connection. But people get it backward. Do I multiply by 180 over pi or pi over 180? Which one is it? So again, I'm not big on which one do you memorize. I'm going to show you how to think it through. That's the key. Think it through. But we are going to make sure we know this by heart. 180 in degrees is the same as pi in radians. That'll be your key. And I think the last thing is linear and angular speed. Linear speed, that's a rate. Speed is a rate. Angular speed, that's a rate. When you do a rate, when you want a speed, you divide by time. How much something is changing divided by how quickly the time is changing. So it's something divided by the rate of change in time. If it's linear, linear is distance. So a linear speed would be distance divided by time. Angular speed. So how bad is the angle? How much is the angle changing over time? So if you have revolutions per minute, that's not an angular speed because all they're telling you is how fast is it turning every minute? What we want to know is what's the angular speed. How many degrees per minute is that mean? Or how many radians per minute does that mean? What's the angular speed? Okay. So we think about the linear speed is the arc length. Now, how much arc, that's where the distance happens along the circle. Distance is out on the edge. That's where the linear speed is at, distance divided by time. Okay? Is arc length divided by time. So you're going to get, and when you do speed, it's going to be like feet per second, feet per minute, miles per hour. It's going to have a unit over time. And when you want angular speed, it's the measure of the central angle, how fast that central angle moving, divided by time. So theta, the central angle measure, divided by time. And theta could be in radians or degrees. It says radian measure. Okay. If you have this, you can just use theta in radians. But you could also be asked, what is the answer in degrees? In the homework, this book does a horrible job of the way they ask their questions. What I don't like is they don't express what units they want their final answer to be in. So it's like, I found out how fast this thing was happening in feet per second. Oh, they wanted miles per hour. Or I figured out miles per hour, they wanted feet per second. On your test, I will always tell you what units I want your final answer to be in, because that's the key. What do I want my final answer to be in? I just got to make sure my units make those units happen. That's how I figure out the problem. What do I want? What do I have? How do I make that happen? That's the key, is to know what you're looking for. It's all about, when we did the speed of light thing last week, it all connects. Okay. And now we get to homework. So 1 through 10 on the homework. Let me see here. 1 through 10 all. And I'm just going to look at a few of them. Just fill in the blank. Measure of trigonometry. The words are somewhere in the text. Okay. If you don't answer all the 10, I'm not going to be too concerned, but math is a language. This is the bread and butter. A blank is determined by rotating a ray around about its endpoint. An angle is determined by rotating. That's the wrong side. By rotating a ray about its endpoint. An angle with its initial side coinciding with the positive x-axis and the origin as its vertex is said to be in standard position. Two angles that have the same initial and terminal sides are coterminal. One blank is the measure of the central angle that intercepts an arc equal in length to the radius 1 radian. So the answer, what does 1 radian look like? 1 radian is approximately 57 point something degrees. I'll show you mathematically, but I'm going to show you right now what it looks like with my crafty drawing. So if I make a circle, it needs to be a good circle. That's a circle. There's the center of the circle. Here's my radius. And if I take the length of that radius, and if I could wrap the length of the radius around the circle at approximately the same length, as the radius is. So again, I took that string, and because I don't have an extra hand, I can't wrap it perfectly around, and that would be a straight line. That's called a chord of a circle. Okay. So I go like that to get it to wrap around. Now I'm losing it, so I've lost it. So it's somewhere up there. So the length of this arc is the same as this radius length, which is the same as that radius length. And this would be exactly 1 radian in measurement. Okay, 1 radian. Because theta is S divided by R. And if S is equal to R, then you just get 1. Now I said that theta is 1 radian is approximately 57 point something degrees. How's this called? Protractor. Well, there's the vertex. And it looks like it's being measured right about here, which I drew it at about 56 degrees. With my crappy shoulder and my crappy arm and my crappy circle and my crappy radius. But that's the idea. Okay. Now, 180 in degrees is the same as pi radians. So what does 1 radian equal? So to get 1 on this side, divide both sides by pi. That's the measure of 1 radian. It's equal to 180 divided by pi exactly. Close my calculator. And so if I punch in pi It's 1.29. Okay. But it doesn't come out to be an exact amount of degrees. Because pi is an irrational number, that decimal goes on forever, it never terminates, it never has a last digit, doesn't repeat. Okay. What does 1 degree equal? So you start with here. You want 1 degree on this side, divide both sides by 180, just 180. So here, 180 degrees divided by the number 180, you're left with 1 degree. On this side, pi, the number divided by 180, is pi divided by 180 radians. So that's what 1 degree equals. It's pi, the number pi divided by 180. And 1 radian is 180 divided by the number pi. Remember, 1 degree, if this is 360, if that's 360, and this up here is 90, and this is 45. And that's a 30. You're talking 1 degree away. I mean, that's probably too big. I'm drawing that big so you can see it in the back. But that's 1 degree, so it's going to be a really, really tiny amount of radius. Okay, that makes sense? Okay, so 1 radian is measured as okay, the blank speed of a particle is the ratio of the change of the central and change of the angle divided by time. So there's only 2 speeds we were given, linear and angular. Which one would that be? It's angular. You're only given 2 different formulas for speed, linear speed and angular speed. So central angle divided by time. So we're measuring the change of the angle, that's angular speed. In other words, because somebody's going to expose you to this, and I don't know why they don't put it in here. They usually do in most textbooks. There's a very set Greek letter that represents angular speed. It's usually represented by the lowercase letter omega. You know what uppercase omega looks like? Oh. No, apocalypse word on his belt because he was the guy. But that's the lowercase omega, or as my physics teacher in high school, omega. I don't know why he called it omega. Maybe that's how it's actually pronounced. I don't have a clue. I always heard it pronounced omega. But it represents angular speed. Formula. So it would be omega is equal to the measure of the angle divided by time. And 1/2 of a revolution. Okay, I'm going to let you finish this. You're supposed to estimate, so you're not supposed to measure it, you're supposed to just estimate the measure of that angle. Now, remember, you're measuring the angle opening in standard position, so follow that red arrow. It's gone past 180 degrees. If you were to, and sometimes you need to draw things that aren't there to help you visualize what is there. That's 180. So you know it's bigger than 180 degrees. So if I estimate this, it doesn't look like, so right here would be 270. It doesn't look like it's exactly in the middle. Again, if I'm estimating, I'd like to estimate really well. It doesn't look like it's exactly in the middle between 180 and 270. It looks more like the one that we did, that was 210 degrees. It looks like this is about 30 degrees past the 180. So I would estimate about 210 degrees. Okay. Any questions? Now, if I had to measure it and actually use tools to measure it, this thing only measures from 0 to 180. But I can do this. I know if I put the vertex right here, that it's pointing right here, and it is pointing at this 150, so it's 150 in the negative direction, but it's also pointing, if you go this way, 0 this way, that is a 30-degree angle right there. So it is 30 degrees past that 181. And then determine which quadrant each one of those lies. And whenever you're asked to put the quadrant, use Roman numerals. Use Roman numerals when you answer that. Okay, now here's something that we did not talk about when you do 17. Also, 11 to 27, every other odd. 11, skip 13, do 15. You're avoiding 17, so actually I don't have to explain 17 yet. But there is something about 17 that really isn't hit much in the notes in this section. So I'll explain it when we do homework problems. So it creeps up in a few more problems as we continue. But this notation right here, this apostrophe, this is 132 degrees, 50 minutes. 50 minutes. And I'll explain what that means in just a few units of time. You do 17, so every other odd, 11, skip 13, do 15, skip 17. So the next one is 19. Sketch each angle. Well, we've already done a pretty good job of sketching our angles. Do 19, skip 21, do 23. When you do 23, 405 negative 780. You can't just draw the angle, and you have to draw the rotation that actually make that angle. So we know that this is 360. To get to 405, you have to keep going. 360 plus 90 is 450. You've gone too far. You've gone too far. So 405 terminates somewhere in quadrant 1. So 405 minus 360 is about 35 degrees past 0. So right about there, and then you label this with 405 degrees. But you have to show that little spiral to show that the opening that made that angle was 405 degrees to make that happen. Okay, and show that the angle happened for positive 405, then it opened counterclockwise. Because when we do this one, you got to show counterclockwise. My bad, I just said it backwards. Counterclockwise because it's going this way. This one's going clockwise. So, got the central angle, right with the initial ray, this side, negative 360, negative 720. To get to negative 780, I just need 60 degrees more, because right now I'm at negative 720. So I need 60 more degrees in this negative direction to get to negative 780 degrees. Can't take 6 from 0, so I got to borrow from here. Oh, that is a 10. That is a 45. Hey, 45. It's right in the middle of it. You are right. Always check on this. You never know if it's testing you, pay attention. There's never is the case. I just know. Imagine if I had to remember that. Because they were at the end of, didn't I earn extra credit on like, it was like January 47th, or there was no 47th, January 32nd, no, there's nothing. January, it was January something, I think, and I earned like 12 points. Yeah, it is. So are we gonna like go back and review? Let's go to the tape. You gotta show direction and you gotta show the rotation. Move. Coterminal. So determine two coterminal angles in degree measure, one positive, one negative for each angle. There are many correct answers. So again, let's see what. 29 to 37, every other, or now odd. Around. 29, no, we're not there. So every other odd. So skip 25 to 27. 300. Coterminal, it has the same terminal ray. 300, I'm visual. I need to see a picture. 300 is right here. So another positive coterminal ray, add another 360. Continue and make another revolution. So 300 plus another 360. This is now 660 degrees. And then one that's negative. So you would want this guy right here. Well, if it's 300 to get to here, this is a 60 degree missing piece to get to the initial ray, initial side. So if you're going in this direction, that would be a negative 60 degrees, or 300 minus 360 is your negative 60. But you could go around 3 times, you go around 4 times. They're all coterminal because they share the same terminal side. That's why it says there's lots of them. And then it goes to 29 to 37 actual odds. So now you're doing the odds. So now I want to show you. I'm going to go straight to the graph and utility, and then I will explain it on Monday on 29. Now I'll tell you what, I'm going to explain it right now a little bit, and then I'll show you, because it's going to take too long to show you what everything is. Okay. So let's look at number 31. 85 degrees, 18 minutes, and 30 seconds. If you notice degrees, you can have decimal degrees. Decimal degrees are DD, decimal degrees. What you're given is, you're given angle conversion degrees, that's minutes, that's seconds. This is DMS, degrees, minutes, seconds. And what you need to be able to do, and I'm perfectly fine that if you just do it on your calculator and not show how it happens, make sure you can at least use a calculator. Convert decimal degrees into degrees, minutes, and seconds, and vice versa. Convert degrees, minutes, and seconds into decimal degrees. We divide the circle into 360 equal pieces. So there's that 1 degree. Now, what about dividing up the 1 degree? Remember, Babylonians love the number 60. So they divide up that 1 degree into 60 tiny little pieces. So there are 60 equal pieces inside of a 1 degree. Those are the minutes. There's 60 minutes in every 1 degree. So 1 degree has 60 minutes in it. 1 apostrophe is minutes. 1 degree equals 60 minutes. And you can keep slicing and dicing. One of those minutes, one tiny little wedge of a minute, can be sliced up into 60 equal pieces. And what do we slice minutes into? Seconds. And there are 60 little pieces inside of a minute. And so there, in 1 minute, there are 60, and that's 2 apostrophes, 60 seconds. Okay. So this would be 64 in decimals plus every 45 degrees, 45 minutes divided by 60 minutes in every degree. The minutes cancel out and you're left with the decimal piece. 45 divided by 60. Now, 45 divided by 60, that's 3/4, right? So this would just be 64 plus 0.75. So 64 degrees in 45 minutes is 64.75 as a decimal degrees. So you convert the minutes into a fraction out of 60. And you tack it on to the whole number of degrees. Now here's where people get a little weird. For the second, so this 85 degrees, 18 minutes, 30 seconds. So it's 85 whole degrees plus 18 minutes out of 60 minutes in each degree. So you convert that into a decimal and you tack it on to the 85. And then you're going to add the 30 seconds. Now we're converting to degrees. There's 60 seconds in every degree, 60 seconds in every minute, and there's 60 minutes in every degree. So how many seconds are in 1 degree? 3,600. Because it's 60 times 60. This one gets divided by 3,600 seconds. And you tack on that decimal part. And you just combine all that and it makes 1 decimal degree, or 1 degree, 1 angle in decimal degrees. And they want you to round to 3 decimal places. That's 3 places past the decimal. So we will continue, going over examples of the homework on Monday. So we take roll. Okay, Roger. And Josh. Here. And Pablo. Here. And Marcelino. Here. And Litzy. Here. And Brandon. Here. Daniela. Here. And Isaiah. Isaiah. And Candace. And Christopher. Yeah. All right, you guys, have a good one. Be safe this weekend and try to get through at least 30, 31, maybe 33 if you can. If you keep on going, 52, do it. Couldn't read, my eye was watering. Okay, Rhett, I'm going to shut it down now.
All right.
Bye.